Hi, everyone. I'm Jung Kim, a second-year master's student at the Harvard Medical School Department of Biomedical Informatics, and also a researcher working with Dr. Yuri Quintana at the Beth Israel Deaconess Medical Center Division of Clinical Informatics. I'll be presenting my and Dr. Quintana's work on the review of the performance metrics for natural language systems for clinical trials matching. Clinical trials offer an opportunity for better treatments to current patients or future patients and advanced scientific research. And for these clinical trials to be successful, accurate and robust cohort selection under specific criteria is necessary. Natural language processing in clinical trials comes in for the cohort selection. The cohort selection can be improved by algorithms that match clinical trials eligibility criteria to data in the electronic health records. However, EHR data and the eligibility criteria are documented as unstructured free text, which makes accessing and using this data challenging. NLP has been identified as a solution to analyze unstructured text and generate structured representations. Algorithms or automated processes that use NLP use ground truth to train, test, and evaluate the model. And human annotation is deemed the most reliable way of collecting this. In clinical NLP, expert knowledge is expected from the annotators, which can be challenging to find, time-consuming, and financially costly. A 2018 study that compared the concordance of an artificial intelligence clinical decision support system, Watson for Oncology, and a multidisciplinary tumor board for breast cancer raised the issue of the absence of a gold standard beyond expert opinion, which can vary profoundly during the evaluation of a clinical decision support. Expert opinion may show discrepancies between reviewers due to inherent ambiguity in the text or multiple valid interpretations, such as how patients with comorbidities and increasing age are treated. Such discrepancy and unreliability of gold standard or ground truth decrease the validity of the performance metrics reported by different papers and make cross comparison of multiple NLP tools difficult. In our study, the evaluation methods of clinical trial matching systems are investigated for the definitions of gold standard, and we urge the need for a gold standard in the patient eligibility of clinical trials and encourage studies to report the agreement score as part of the performance metric. In May 2021, PubMed ACM Digital Library and IEEE Explorer were searched using the query, clinical trial matching, and natural language processing and evaluation. Science Direct was searched using the query, clinical trial matching, and natural language processing. The queries were used to search against all fields in PubMed and title only in the other three databases. We only consider the articles published between 2016 and 2021. The papers were filtered if they did not directly evaluate the performance of clinical trial matching systems. Then a total of 5 articles were reviewed for 4 main pieces of information. First, clinical trial matching system used. Second, performance reported, such as the metrics recall, precision of measure accuracy, and specificity. Third, the definition of their gold standard. Fourth, any reports on their agreement score. If the gold standard was explicitly defined in the article, the reviewer's expertise, whether they were clinicians or non-clinicians, was also noted. A total of 5 articles were evaluated for the performance of clinical trial matching models. 2 articles used the IBM Watson for clinical trial matching. 1 article used Consem2Vec, and 2 articles used unnamed models, one of which was a machine learning classifier with named entity recognition, and the other was an SVM classification method. All 5 articles reported their gold standard or standard reference definitions, but with varying methods and levels of expertise. Manual review was the most common method of defining the ground truth. Of the 5 articles, 4 articles conducted manual reviews by multiple raters. However, not all studies that use multiple raters reported coherence kappa, which measures the inter and intra-rater reliability. Furthermore, the number and the medical background of these raters were diverse and inconsistent. The raters range from as general as annotators, trial team trainees of the informatics program to clinicians, nurse coordinators, oncologists. One article by the Medical University of South Carolina in 2019 had a unique definition of the reference standard, which was the original clinical enrollment status of the patients. Two articles that used IBM Watson for clinical trial matching did not share the same gold standard. Alexander et al. Had two clinicians manually review the patient trial matches, while Beck et al. Did not specify the number of reviewers nor their expertise. Such an approach of obtaining the ground truth from domain experts is costly and susceptible to poor quality because recruiting experts to label data and training them is financially costly, and labeling and annotation are a highly time-intensive process. Furthermore, the process of eliminating a disagreement between reviewers may introduce artificial data that is neither general nor reflects the ambiguity inherent in natural language due to the use of overly prescriptive annotation guidelines. While manual review has its shortcomings, it is important to acknowledge the role of humans in natural language processing. After reviewing the articles, we suggest two approaches of defining the gold standard while utilizing humans, but in a more scalable and cost-efficient way. As a 2019 study by the Medical University of South Carolina has defined, small-scale studies should use the patient's original clinical enrollment status as the ground truth, as it is objective and free of reviewers' bias or interpretations on patients' eligibility. For larger scale studies that look at larger number of trials, an automated process for generating ground truth will be needed to produce training data that are scalable to the model size, considering the cost and the unscalable nature of a manual expert review. It will still require human input to develop and streamline the process, but more efficient than to simply scale up the manual review. While there was heterogeneity in the medical knowledge across reviewers in the 4 papers that utilized manual review, recent studies found that crowdsourcing from ground truth produced the quality equivalent to what the domain experts would produce. In a similar context, once experts created a guideline of matching patients to a trial based on similarity scores, an automated algorithm such as the recurrent neural network could generate similarity scores translating into ground truth. This automation will help obtain a large training data set for large-scale studies. Moving forward, it is essential to devise a rigorous gold standard that is used by all trial eligibility matching algorithms to evaluate and compare results and to create more generalizable methods. The future work I like to see is a more comprehensive review of clinical trial and patient matching algorithms, exploring queries that are more inclusive and search terms that could potentially be related to the gold standard could broaden the search and provide insights in the best way to set the gold standard. Today, I talked about how the gold standard should be defined, but once the gold standard is defined, there can be management issues of the maintenance of the gold standard with the constant addition of medical knowledge, which should also be of active conversation. The nature of clinical narratives as a sublanguage makes it difficult to apply NLP trained on general text and requires domain-specific development and training. Furthermore, considering the diversity of electronic health record systems used across hospitals, generating training data and ground truth requires study-level efforts. Therefore, a single definition of ground truth must be used across studies to compare the NLP tools developed. Sharing the annotation of each study can promote building larger training sets among hospitals that store free text patient information similarly or use the same electronic health record systems. In the future, I hope to see more studies that directly compare existing trial matching systems that use machine learning and natural language processing, and see more active use of NLP in clinical research brought by more readily available public and robust data sets. Thank you for listening.